our class already introduced you at the other Institute in Germany, and today I'm going to talk about electromagnetic counterparts and sporadic geometry of binary black hole mergers. These are basically two of the main topics that I've worked on during my PhD. They're both made of numerical simulations, and I'm going to try to give you a quick overview of what it's all about. Okay, so the first part of the talk is about counterparts of binary black hole mergers. How actually is basically the expert in all of that. We've done actually quite a lot more recent work on that. I was sort of say part of the first round. And so why are we interested in electromagnetic counterparts of binary black hole mergers? So these supermassive black hole systems that we have in mind result as basically a system by two merging galaxies. So we know that most of the galaxies have supermassive black holes at their center. Like it's well known for the Milky Way galaxy, for example, and we actually can constrain the mass of these black holes quite well. And so two galaxies, from the population studies, we know that galaxies undergo mergers actually at certain enough rates. So if these galaxy mergers and they host supermassive black holes at their centers, then at some point also the two supermassive black holes are likely to merge. And so what can we learn from getting electromagnetic information also from these mergers? So these are very likely sources for gravitational wave detection. So supermassive black holes, for the ground-based detectors, they're not optimally in the frequency band, so for missions like LISA, which are also a little bit in doubt, recent budget cuts, but we still hope that LISA as a European mission or maybe later as a joint European US mission will fly. And then these are prime sources for the detection. But from the gravitational waves, we can only learn a certain amount. And if we can also have electromagnetic observations from these sources, we can learn a lot more about the source, can constrain its parameters a lot better. So that's why we actually in a ideal case want to have both information, gravitational waves and the observation in EM waves. So this is basically the motivation why we want to look at these systems. And why can we model it like the way we model it here? So you basically start first on the left here in this panel. So basically you have the two black holes with their own accretion disk, still very separated. So they both have their own accretion disk. And as they inspire and get closer together, at some point the gravitational wave emission is going to take over and drive basically the system in the final part of their coalescence. And in this case, at this part, we're going to form a binary, and any leftover material in the inside, in the vicinity of the black holes, will be expelled. So you form a certain binary disk, and you can model the binary in the center with maybe only very, very low density gas around it. And so actually the model we have in mind is the very first, a very crude approximation to this problem is we take the binary and we assume that the disk will have a magnetic field in most cases. So this magnetic field will also reach the binary in the center. So in our model, we basically neglect any matter that's still around the black hole and just assume a magnetic field assumes to be anchored at the disk. We don't actually include the disk in our simulation. So we basically have a binary immersed in a uniform magnetic field. And the uniform magnetic field, we assume that if you would have a dipolar field from the disk, if you're looking only very close in the center, you can, in a way, approximate it by a uniform field. So to model the system, since you're interested in basically the full GR part, we actually use a full 3D GR code as typically used in numerical relativity. So we have Einstein's equations, which are here. We have on the right-hand side the stress energy tensor, so basically any matter source or radiation source will also be coming in. And now we couple it to the Maxwell equations to that. So we have a Maxwell-Einstein system, and this is what we solve. But the Maxwell equations, later on we will simplify it with our assumptions, so that our model is actually possible for our simulation. Right, so if we do that model,
if we go back to
yeah, sure.
So I guess
constraints on the controlling or resolution which might blow up the numerical instabilities in the system. So basically these are added artificial fields that have no extra.
So what equations do they obey?
Oh, this will be on the next slide basically. So you get evolution equations for them. So if you concentrate here, so at first we have evolution equations for electric and magnetic field. These are the top two equations, and then we get evolution equations also for extra quantities of sine and phi. And if you look at it, then this is basically like a damped oscillation, so it basically tries to keep the constraints under control. And so here now, this is the system we actually get for this is the Maxwell system we formulated for evolution equations. And you have evolution equations for the electric and magnetic field, and then coupled in are these extra fields that are used for the constraint damping. On the right-hand side, you basically have the sources here, and I just would like to concentrate on, so here you have JI, which is the free current, and then you also have Q, which is the charge density. And I have written these equations now for a more general case, which is called the force-free approximation, which Carlos has actually done a lot of work in. The result I'm going to show, actually, we set those terms to 0. So the current is 0 and also the charge density is 0. And this corresponds to a case that's called electrovacuum. So you get the radiation here, you actually don't have any real electromagnetic sources in the system. So this, also here, the expressions for Q and JI have just written to close the system here correctly. Those are, for the results I'm going to show in this talk, they're set to 0. So we're operating in electrovacuum. Okay, so the first thing we were interested in are basically a way simpler system, single black holes. So what can we do about single black holes? First of all, they're actually the end result of our mergers. So in the end, we end up with a single black hole that might be spinning in some sense, and this is actually the likeliest scenario from a typical binary merger. So for single black holes, we actually know an analytic far-field solution, which was introduced by Wald. And so we can actually try to see if we obtain this solution when we do our numerical simulation. This is the test for our code. And so in the bottom part here, you see the field configurations that we obtain. So in the black sphere, basically is the black hole apparent horizon, and then the gray lines are the magnetic field lines, and in red you see the electric field structure. And so this is now for this on the left here is for a non-spinning black hole. So in this case, you can actually perfectly obtain the solution that was described by Wald. And then going to the right, here we have a spinning black hole. You can see that now the spin effect actually twists the electric field lines. It also twists a little bit the magnetic field lines, but it's not as obvious as in the electric field. And then this is the spin here is the line with the magnetic field that we choose. So this is the spin with the something like that. And on the right, you see how the solution looks like for a spin that's actually anti-aligned with our magnetic field. So here we take basically the maximum anti-alignment that we can obtain with like a 90-degree angle between the magnetic field and the spin of the black hole. And in this case, you can see that actually this twisting gets a lot more deformed here. So from that already we know that spin will determine somehow the structure of the EM fields that are close to our black hole. So now let's go to binary black holes. That's basically in the end what we're interested in. And so we can also look at these field line configurations now during the in-spiral and during and after the merger of the typical binary. And so there are basically two effects that we mainly see. One is that the orbital motion of the binary as it spirals has an effect and drags the field lines a little bit along. And so basically there's a deformation of the field lines due to this effect. And on top of that, then if the black holes are spinning, you get this extra contribution that we were already seeing for a single black hole. So if you look at this here, it's again the magnetic field is in gray and the electric field is in red here. And these are the two black holes during the spiral. And you can basically see now that this looks a lot more complicated than for the single black hole case. And you have basically both of these effects. This is for a two spinning black holes where both spins are aligned with the magnetic field.
What is the initial field configuration?
The initial field configuration is purely uniform and actually along the z-axis in our Cartesian. So we have a purely Cartesian code that we use, and this magnetic field is in graph. So here, the spins are basically aligned with the magnetic so we don't actually do any special also boundary conditions. We basically just want to not introduce any extra EM radiation around the boundary conditions. So yeah, in this case we actually use the same as we use for space-time variables. So in that sense, they are simple radiated boundary conditions.
And the boundary is specially connected, or
so
also
this,
connected?
So here so we make sure that the boundary is causally disconnected from in the end we want to get luminosity estimates of our EM waves that we generate. That will come to that in the next slide. We make sure that the boundaries have no effect on the data that we want to obtain on our detector. And it takes some while for the system to establish the detector. Basically the same as for gravitation. Yeah, our boundaries are not perfect in that case, so we have to make sure that they're causally disconnected. On the right now, you basically see a configuration that is obtained after the merger. So this now is a single spinning black hole. This is what the stationary state is that we set it down to at some point. So this is spinning, and you can basically see that this looks quite close to what we were seeing already for just starting either as a single black hole. Okay, so now we can basically do a bit more fancy and look at what is the EM radiation that is generated by those systems. And I start off with a movie just to give you an idea. So on the left here, you see, so there's actually two black holes that are at the moment just sitting behind each other, so that you only see one. On the left is highlighted the EM radiation, so just some quantity here. We call phi 2 when we take the imaginary part, but this is mainly for the visualization here. And on the right, you see something representing the gravitational waves, which is the quantity called psi 4. And we also take the imaginary part just to show you that actually the emission looks quite the same in both systems. Let's play that now. Basically, now you see the two black holes, which are here the gray spheres in spiraling. During the inspiral, you see a more or less constant field, but this is also part of what we choose for our visualization, which we later on want to highlight on the emission that's happening during the merger. So they get closer and closer. In the top left corner, you see the time as measured in our period unit m, so the mass of the black hole. Here we quickly stop the simulation for a second and close before merger and just zoom out so that you get a better overall picture of what's happening. So now the time goes on again, and you see that basically the emission in both systems actually looks quite alike. And then these rays propagate outwards and reach our detectors that would be located somewhere here. Okay, so now we want to look at how we can analyze these EM radiation in some more detail and correlate to the gravitational wave signal that we obtain. So, for getting the fluxes of energy that we emit in both systems, in both bands, basically for the gravitational waves, it's quite standard. We take a quantity psi 4, which is the complex scalar associated with the Y scalars that basically represent outgoing gravitational radiation. We integrate it over a sphere and then also in time to get our signal. And we can do something similar for the EM waves. And there's a quantity called phi 2, which basically represents outgoing EM radiation, and that we can also obtain and then integrate over a sphere to get basically the emission, flux of emission at time. And then we can look at this, how these things evolve in time. And so here in the top, in the bottom panels, I show on the left actually how the waveforms that we typically obtain for gravitational waves look like for different systems. So we're interested, we've already seen that we use different spins, and they have an influence on the field structure, so they will most likely have an influence also on the EM radiation that is emitted. So what we look at here are different spin configurations, and we've chosen only certain angles of alignment or misalignment. So we've taken where both spins of the black holes are the same magnitude, and they are both aligned with the initial magnetic field. Then we take one where both are anti-aligned, and then we take a mixed configuration like that. And as a reference point, we also take the non-spinning binary system. And these are basically the four different colors that you see here. So the black one would be the non-spinning, The green one would be the mixed configuration. The red, where both spins are anti-aligned to the magnetic field, and the blue one would be the one where both spins are aligned. And you can already see that basically the peak values that we reach for the systems in these waveforms are different. And on the right now you see the same for in the EM band. And here it's a little bit different since we rescaled that. So this is the signal in the EM band is a lot weaker than in the gravitational waves. And so we have to rescale it. So the differences here are not as obvious as in this system, but basically you can see that the two of them actually match quite well and how the difference in the experiments on the peak value of the waveforms. Alright, so if we thought we want to have a closer look at the correlation, that already looked quite obvious from just looking at the signal, but we wanted to see it in a bit more detail. So what we looked at was the amplitude and the phase evolution for one of our binaries. And so here we first now take the most dominant mode, which is the 2-2, the L2 and 2 mode, decomposed in spherical harmonics. And then if you look at here the amplitude plot, so we have to rescale the signal in the EM band to match our signal in the gravitational wave. But if you take even a constant rescaling, basically these two curves lie nearly basically perfectly on top of each other. So these are very well correlated. And also if you look at the phase evolution, this also lies perfectly on top of each other for the two signals. So basically the two signals are very, very well correlated at least in the dominant mode of our system. If you would go to higher mode, we also looked at this, for example, if you take the L3 M2 mode, then you can still rescale it to match an amplitude, but you need a rescaling factor now that varies in evolution time. So it's not as good anymore as for the L2 M2 mode. The phase evolution still matches very well. So the message to take away from this point is, if we could actually detect a coincidence in both bands, we most likely could correlate the signals quite well and actually identify them to the same source quite easily. So now looking a bit at energies, we were asking ourselves how efficient is the emission we see. So we already saw in the waveforms that the signal in the EM band is a lot weaker than in the gravitational one. And so if you look at this very closely, of course the emission depends on our initial field strength for the magnetic field. So we put it as an initial condition. So that's why you have to scale in here the superlative magnetic field. And of course it also depends on the total mass of the binary system. And then if you look at the emission in the EM, it's 10 to the minus 15 here. And if you would compare this now to the gravitational wave emission, since we know that this is up to a maximum of 10% for the most energetic spin configuration, then you see that actually the emission in the EM compared to gravitational waves is like 13 orders of magnitude smaller. This at first looks like, okay, this is so small, but then you have to take into account that for these supermassive black hole mergers, there's like a system mass of 10 to the 8 solar masses. Actually, there's a lot of energy released in gravitational waves. So even if this is only a 10 to the 13th part of it, it still might be detectable in some way. And so in the plots here, you see basically the energy flux obtained from these waveforms that we looked at before. Now you see basically that in both bands, rotational waves and EM, the energy basically scales in the same way between the different spin configurations of the system.
How do the scales in these plots square with the 10 to minus 30 you mentioned as well?
So this is basically...
I'm wondering about the scale factor for magnets in the left plot and to the 7 on the right plot.
Oh, so basically, so this is, here we basically for this we only take the quantity, because now you have to actually take the absolute value squared to get the luminosity in the end. So then you get from factor of 10 to the 6 to the 10. Okay, so okay, we can still look at if that is detectable in any way. So two main things that we looked at is, like, first of all, what variability is introduced in the EM fields, what is the frequency? And if you see from here, these frequencies are very low, so they're outside what is accessible to radio observation. And then the luminosity itself, which is here. So for like this is done now for 10 to the 8 solar mass black hole system, just as a simple example. And of course here again we have the scaling with the initial magnetic field. So for like a system for 10 to the 8 solar mass black holes, you would get something like 10 to the 41 ergs per second. This would be visible if it's very close by, but then you have to also think that you have the accretion disk around. So you have to think of what emission do we get from the accreting material itself. And so then if you compare it to the Electron luminosity, then you get that this is only like 10 to the minus 4 compared to that. So only if you would have a system that's accreting at very small rates or not at all, you would have any chance of seeing that directly. So combining both of these things is that it's very unlikely to be detected directly. On the other hand, there still might be a way of influencing the accretion of the disk, since you have in the end a variability in your B field, and this also will be felt by the disk in some way. And this is actually like 10%. So if you look at how the initial magnetic field varies, if you look at the inner radius of the disk that you assume somewhere, then you would have still like 10% of the initial value in these variabilities. So that might well be possible. So you can compute what the EM energy flux, which is reaching the accretion disk at its inner edge, is, and you would get something like what is here, 10 to the 11 ergs per second for 10 to the 4 Gauss magnetic field. So can this actually influence the disk at all? So if you would, so in a very crude approximation, we just wanted to compare the viscous transport and the magnetic transport timescale to have an idea if that has any effect. And so let's say you end up with this formula here. And so here the parameter beta is measured for the distortion in the magnetic field that we introduced. And alpha is the standard disk parameter. And then CS here is the sound speed. So then we looked at the range of parameters that we have available. So for these values that I report down here, like the 10% is for the magnetic field, and then the sound speed we take into account here. Actually, we find scenarios where it might be possible that we actually alter the accretion rate of the disk, and if that has some typical variability, we might be able to detect it basically indirectly. If the accretion rate of the disk is stable enough that we can identify the signal on top of it, then we might have a way of like seeing this. Okay, so let me summarize the first part of the talk. So we've analyzed the phenomenology that the spiral and merger of black hole binaries in uniform magnetic field, which is assumed to be anchored as a certain binary disk. So basically what we can show is that the orbital motion and the spin of the black hole distorts our EM field, and by that also introduce EM waves that we can try to detect. The main message is that in our very simple model in electrovacuum, it's very unlikely that we can detect this emission directly, but there might be this indirect way of detecting it when it can alter the accretion rate of the certain binary disk. So for some future directions, we're also planning, actually doing it at the moment, simulations in the force-free approximation, but this is very recent work in progress, so it's also a little bit too early to present it here. And then another thing is to go to a different magnetic field configuration. So maybe really go to a dipolar magnetic field and see how this changes our luminosity that we obtain. Okay, so now let me switch to the second part of my talk, which is on a topic that is still related to microrelativity, but basically at the other end of not connecting to astrophysics, more connecting to mathematical theory. And so in this I'm going to talk a little about how the horizon geometry in like a typical black hole merger looks like. And here we're interested in how this happens in the very late stages. So just before we form so the merger of two black holes, here we take just a head-on case. They approach each other, at some point they get close enough so that we form a common outer horizon. It's basically it's from the outside then everything that we see. This is our final black hole, but the surfaces that represent the individual horizons still continue to exist and they interact. So we want to know what happens to these surfaces and how do they interact in terms of their geometry, do they change, when do they cease to exist, and how does this go about? So on the left here, you see basically a sketch of how such a merger might go about. So here, from the bottom part, you see the two individual surfaces coming in. So basically these are represented here as just lines, and then their time evolution is basically the tube they trace out here. So at this point you have the two individual black holes, and they evolve in time. At some point they get close enough, and you see here the common horizon is formed. But the individual ones will continue to exist. And from mathematical theory, there's quite a bit known about what the evolution of these outer horizons looks like. But we cannot say much about what the individual horizons do after we have formed the common one. So this is something we can, of course, do with numerical simulations. So we thought we can have a look at this and maybe highlight something that's not accessible to mathematical theory about these surfaces. And so we looked at an unequal mass binary black hole merger, but in this case this time they're not inspiring, they're just approaching head on. This is our simplest scenario, and even there the geometrical effects that we see are already quite complicated. And so what we want to know is what happens to the individual surfaces after a common one is formed, and then also extract some information about the common horizon. The common horizon is, when it forms, it actually forms as a pair of two surfaces. So we have one that is stable and that grows outwards and forms the common outer horizon. Then we also have like another one that shrinks inward. This is unstable. It will try to wrap around the individual horizon, but at some point it might also stop to exist. So we can extract information about all these surfaces and try to see how the time evolution looks like. So just three equations to give you some basics about the theory that we're using. So we find these horizons by searching for an equation that's called the expansion equation. And you have basically, you set this to 0, and then by that you define your surface. And this equation has two contributions. It's P and H here. And H is the mean curvature of our sphere S, so basically our surface, in our slicing. So the slicing is what we typically do in numerical relativity for those who are not familiar with this. We basically decompose our 4-dimensional space-time into a 3-dimensional space-like part, and then we separate the time evolution into a slicing of these spatial parts. And so basically, the first part here tells us about how our sphere looks like in the slicing that we've chosen, and then the second part, now here the P, tells us about what have we chosen to do this slicing in the first place. So we basically have two contributions to represent the full information in 4D. And one is the sphere itself, and then the second is the choice of the slicing where we represent the sphere in. Right. So here for the space-time evolution part, we use a slightly not so standard evolution code. We use something in which is called the harmonic formulation of the Einstein equation, so the not so standard basically is the point of interpretation of both systems they use. So basically these are our evolution equations. So here you see the metric of the space-time, and you see the quantity that is called the shift vector and the lapse function, which basically give you an idea of how your points in your slicing that you've chosen evolve from one to the other, and how the time elapses in our numerical simulation. Right. Now we start with some features. So this would be a typical initial configuration that we look at. And here you see that basically the two blue spheres are again our horizons of the two black holes, and you basically see that like there's a mass ratio here. The mass ratio for this simulation would be 1 to 4. You see that they are from an axisymmetric system here. They approach along the x-axis, so basically they would form a common horizon somewhere here. Initially, we already choose our black holes to be very close together, since we're only interested in the last part of the merger process. And our black holes have, in this case, no spin and also no extra linear momentum, so they basically just put them there and they start to merge. So now we look at what can we see in our simulation. So we have basically 5 distinct stages. There's a large separation part where basically the properties of both black holes can be looked at as an individual system. They don't influence each other in terms of their geometry. Then eventually, as they start to approach, at some point they form this common horizon. And at this point, this is when it gets interesting for us. But then we don't really know what's happening to the individual surfaces anymore. And then basically these two surfaces continue to approach, and at some point they start touching. And this was an unexpected feature that actually no one was expecting from these numerical simulations. This was first seen by another evolution code of another collaboration. And so basically this is something we wanted to confirm, and we actually can show that. They basically start, at some point they touch, and then they start to overlap. And this is the next part of our simulation, where these two marginally outer-trapped surfaces here is just a word for another synonym for the horizon of the black hole in that sense, the two surfaces that we're looking at. And in the end, we're also interested in what ultimately happens to our individual surfaces. How do they form the common one bit?
So how can I just ask a simple question?
Yes.
So I have these two things coming together, and the horizon. Am I allowed to think of the horizon as getting highly distorted?
Yes.
And is that the reason that they form a modified common horizon before you would have said classically that the two horizons would touch?
So they certainly get highly deformed, but this here is mostly because we have an unequal mass simulation. In the equal mass case, I'm not so sure if that actually still holds, but I'm not sure if the common horizon can be tied to the tidal, so the formation of the common.
Let me ask it then, what is the shape of the common horizon before they quote unquote touch?
Okay, so the shape of the common horizon starts off quite not as a typical sphere, but more as a peanut shape. So you can basically, if you look at two equal mass black holes here, then both of these individual spheres look like the same radius basically. And then you would have like a peanut shaped common horizon wrapped around them. So it starts off in a very, very non-spherical state and then relaxes and in the end forms this standard common horizon that then becomes spherical. So this is how they start off very distorted. And this is also true in the case we are looking at.
And if you were looking at the other side, the far side of the horizon, does it actually get relatively pushed in relative to the standard one again?
And so by far side you mean
that
this
side.
here?
Yeah. Does it get squashed in a bit because it's trying to find a new common center?
No, actually I don't think this happens. So we can see, and this is actually something we showed here on the right, that actually this side of the larger individual counter horizon gets distorted by the small one approaching as a tidal effect. But on the other side, I don't think we actually see something special happening. Okay, so basically as they approach now, the smaller counter horizon here has a tidal effect on the larger one. And so it's not obvious from these coordinate representations that we choose here, but these are not invariant properties. They're very much depending on our choice of the slicing that we do. So they can look very different and don't really tell us something about what's going on in the geometry. But you can look at some of the geometrical invariant properties, like for example this contribution in the CITA equation that I've shown you before, how we find the horizon. This is called something like the mean curvature, and this actually is not dependent on the slicing. And this is something I showed you on the right. Basically now you see as a function of this angular coordinate system of the horizon, you see the mean curvature. So this is the H here on the left. And this is now for the two different surfaces. In blue you see the mean curvature of the larger one, in red the one of the smaller one. And initially they start off basically as a flat shape. And they're different because they are unequal mass, but then you see that while the small one approaches, actually the bigger one develops a tiny distortion. This is basically here this little peak that's starting to develop.
So this is the mean curvature of the S2 surface and that in the minus.
Exactly. So if we would go back here, so the H is the mean curvature of S embedded in the Cauchy slicing. And this P quantity here actually is both the same since they're both embedded in the same slicing. So the only thing that can actually be different is the H.
And H is independent
So at least the relative change in the age, from the absolute value is not independent of displacement. Since you have the contribution here of the true, yes, the age actually is not geometrically invariant property. The relative, so what we're interested in is basically how the change happens between the two surfaces. So, and there the age, of course, is more interested than looking at the coordinate shapes. So it tells us about the geometry on the sphere. So yeah, actually, that's a good one. Okay, so here we see the tiny effect of the smaller one coming in. And now they continue to approach, and this is now at the point where they first touch. So if you look at the coordinate representations here on the left, you see that basically now the two surfaces here actually touch at some point. And at this point, mathematical theory tells us that the mean curvatures, at least at the point where they touch, where they first touch, they have to agree. This is known from analytical theory. And so actually we can nicely show that this actually happens. So now this is later in time. The peak in the blue here has risen even more, so that it matches now the red in this one point where they match. And this was, first of all, a very nice confirmation of what the series has, and actually confirmed this with simulation. So we're doing something reasonable with those simulations, and then this already gives us some idea of if we can trust it or not. So now we're interested, how does this continue? And so in the end, we end up with a scenario like this. So now basically both surfaces overlap and intersect each other. And so this is a picture at nearly the end where we can find these horizons for the last time. And so halfway into the larger horizon. And at this point, since this is a feature maybe for initial data, so we use basically a type of initial data which is called puncture initial data, where you don't do anything. So we don't do anything special to shield off the singularity that's contained in the black hole from our system. So as you would expect that the coordinate singularity would be somewhere here in the center of our sphere, and this now starts interacting with the surface of the other horizon. We're not anymore sure we lose the horizons here because the puncture starts screwing up, basically by having more or less infinite values. They're screwing up our numerical calculations. And that is where we maybe lose these larger surfaces. And this is what happens to us in the end. But still we can learn something from that looking at other quantities. So here now we look at the area evolution of both of these black holes over the evolution time. And so on the left you see the area evolution of the larger current horizon. And what is interesting here is that we actually get a jump in it. So at first we were not sure if that is just a numerical effect, but we've actually checked this at different resolutions and also different time resolutions to see that this is really a discrete jump that is happening. And then we checked back with our colleagues from mathematical theory, and they basically say that this actually can happen. So what is happening is that the time evolution of our current horizon just intersects the slicing that we've chosen twice. So that is possible, and then you can jump from one solution to the other. And this is exactly what we see here. So basically we jump from a solution that has an area here and actually starts smoothly growing to another one which actually has a different gradient in the consequent evolution. And this is something that doesn't happen for the smaller current horizon. So this is also connected to the tidal effect that the smaller one has on the big one. And actually, so later in another simulation we see a second jump in our higher resolution simulation, and we're trying to actually make sense of what this might mean for how this detailed merger in the end goes about. Right, so going back to one of the questions we wanted to answer, the ultimate fate of these two individual horizons. So what happens? And so this is something we cannot really answer at the moment, but we might speculate about it. So we see this jump in the area, and we also know that we lose the larger current horizon at some point. And so the scenario, if I go back to the sketch here, is that there's some idea that these two individual horizons actually connect via this dotted line here to the outer common one. And this actually this jump is kind of an indication that we might move in that direction. Right? We would need to run other simulations and maybe refine our numerical techniques to really answer this question in a way that we can trust. And at the moment, it's just a speculation. But this would be interesting, especially also for theorists working on the mathematical theory of these surfaces. Okay, so let me also summarize the second part of the talk. So we've analyzed the geometrical properties of our Lagrange horizons in unequal mass binary head-on mergers. And so we basically investigated how our geometrical properties of these surfaces evolve in time while the merger goes about. And so one thing that we show and find is that there's a strong tidal effect of the small surface on the larger one. And then the other thing is that we can actually find the two surfaces until they're nearly, the small one is halfway into the big one. This is something that hasn't been done before. So basically before there was only the point of touch that was shown. And so then it still remains kind of unclear how the detailed merger in the end of all these surfaces goes about. But we might have already found some clues how this might happen in the end. Thank you for your attention. Yes.
Should the magnitude of this jump in the area depend on your choice of slicing?
The magnitude most likely will depend on the choice of slicing, since already the jump at all depends on the slicing. So you can find slicings, so basically the jump doesn't happen because it doesn't intersect twice. And so the magnitude also will depend on that.
So this jump, I would conjecture there are actually two more apparent horizons behaving something like this. That's at least what Tony Chu found when he looked at single and black holes.
Yes, so this is basically now, if we find these horizons by searching for the function equation equals 0. If we would slightly modify the right-hand side of this equation, we might be actually able to find these other branches of the surfaces that to connect basically, to get rid of the jump and basically connect it to different paths. But actually in these 3D simulations it's not so easy to do. There's a lot of trial and error to get the right, you need an initial guess for the surface you want to find, and this to get correctly is a little bit of guesswork.
Can you save the volume data for your space-time and know what the current horizon can get backwards in time?
Yeah, actually this is something I discussed with Eric on Monday. This is something I actually want to do next. So let's just run the horizon finder on the individual parts of the run that we are interested in.
That's what
Yeah.
So I'm sorry, so can you follow more complicated things with topology? Or I didn't quite
So
get what
this-
you said.
there's a theorem around, I believe, that the broad tubes being traced out by marginally cut surfaces must be smooth. And so the way to turn this into a smooth broad tube is to actually have this one here turning over and come attaching back up there.
Okay, what is the actual vertical axis? Is the area?
That's the area. So then, at some points, we'll have even more marginally cut surfaces than already there.
Yeah, so basically what Harald was depicting here is if you would turn this back here, so then you would do choose one time, you would actually have two surfaces existing at the same time. And this is how you could smoothly actually continue the two I'm showing here.
So you're saying that in effect, I mean, these two surfaces, one in the other?
Yes.
So,
Yeah, so inside these common horizons that has formed already, there exists actually not only one or two surfaces, there actually exist a lot of them. So finding them is difficult, but if you could actually paint that into a smooth picture.
What is your H?
Oh, this is run in pure harmonic gauge. So basically the evolution system is a harmonic system, but formulated in the 3+1 variable. So we evolved the 3 method, lapse and shift. But for the single black holes and head-on, we can actually run in the pure harmonic gauge. So the source functions are, gauge source functions are purely 0.
And so you, at that time when you stop the simulation, the current horizon point that crashes or the actual evolution?
No, the evolution doesn't crash. So basically our evolutions are actually so once we actually have lost both horizons, and basically the common one has set it down to its basically its astrophysical solution, we basically stop the simulation completely.
So the simulation comes first and then the last one.
Yeah. Yeah, actually, so we've done tests for this code also with single black holes, so you can work for as long as you want to. So yeah, in the numerical sense, the only thing we have to do, which is the trick, is that we offset our puncture from the grid point. So you don't put the puncture itself on the grid points. But for the harmonic system, it's a bit more difficult to actually get the punctures working. So if you're not using a signal or anything. Any more questions? Yes.
The similarity between the electromagnetic radiation and detectable basically comes because the horizon act like four electrical conductors that are spinning black hole and polarized and get a quanticle, electric quanticle, and then you have a quantum-dependent quanticle. Is that right? And so it's basically quadrupole radiation from gravity, quadrupole radiation from electromagnetic field. In a sense that they're very similar.
Yeah, so basically what you said is, in that sense, correct. So the dynamics that are in the system is purely from the gravity. So basically there's nothing else coming in. And then you can, so there's this nice thing called the membrane paradigm where you can also, where you can basically relate the effect. So basically what you said is actually how you can see it.
So then when you have, because of the conductivity, effective conductivity of the membrane is low. It's a free space for heat. When you have a time change in the horizon, if you're very in a magnetic field, yes, in a vacuum magnetic field, you have some complicated motion, and you have more complicated than this. Then there's some adjustment, there must be some factor to the adjustment time. That conductor embedded in a, which is having a time-dependent exposure to the magnetic field. That's why it's difficult to grasp, but I have to think about it a little more. But it's as though you had a small with a battery for electric conductivity, and so the magnetic field was fused into it in a very, very short time. At the same time, it's always changing properties or orientations of the field, so you would be getting complicated quanticle.
Yeah.
Must be something like that. It must be possible to, I guess it's not possible to get a dipole, it's like a quadrupole without a four. With your geometry, you only have quadrupoles.
Yeah.
But I don't know whether any more general dynamics with dipoles is that makes it very easy to get. Far field radiation dipole, or whether there's a theorem.
Well, if you have the black hole spinning and then the field, and they're not spinning parallel with the background field, we get back around, I think we get some black hole radiation.
I think there is if you consider an equal mass case, each black hole will have a dipole that if the masses are equal, the velocity, because the velocities are equal, they will cancel the dipole contribution and you will have only quadrupole. But if you have a mass ratio,
You can actually get dipole radiation. So that boosts up your efficiency quite a bit. I mean,
yes. Well, that is what we expect, but no one has proven it yet.
I mean,
you have to boost the efficiency in some way, so the dipole might be a good combination to do it.
Is there any other questions? Otherwise, we can continue the discussion after the show.
You know, the difficulty with seeing the magnetic signal from this is just that the energy in the magnetic field as imposed in black holes is very small compared to the rest energy or the binding energy, useful binding energy of black holes. And so one can ask physically, are you missing something? And this is just a little, up in left field. But supermassive black holes, most people think, are accompanied by swarms of stellar objects, right? And some of those are going to get kicked out very fast. So if you're setting off, pencil and mass stars at the speed of light through the astronomy medium, the question I leave to you is that practical? I mean, not even you think the faster star moves, the slower it accretes, but it's moving at the speed of light, close to the speed of light. There's much more mass. There'd be much more mass in this than there would be in, this magnetic field. It's going to be appreciated.
Just repeat to get your. So you're saying that basically you will have like stellar mass black holes moving at a very high speed, close to the speed of light.
Yeah, some will get eaten by the two trilogy supermassive black holes, and some will get kicked out.
And so basically, your question is, will those be detectable, although they basically won't be surrounded necessarily by inclusion?
And that's sort of wild from left field thing. But the other thing, more closely tied to what you were just calculating, keep in mind is that there will be very long-lived, either of these black holes producing jet, of course, will be very long-lived structure in that outflow that would be much easier to see. Because long after the merger, you could tens of thousands of years, you could see that. And I suspect that would be the way if you would look at the electromagnetic